All right, welcome back. We are Game 3001 in the winter 2021 semester. And I'm Tom. I'll be your professor for today, as always. And it's week 8, part 1 of our broadcast. Today we're talking about decision making with AI and decision trees. But before we get to that, let's get into what's happening from an admin perspective. All right, this week, Lab 6 is due this Sunday at midnight. Okay, a couple of notes from Alex, who's marking the labs, is please make your repo private. Please forget not to do that. Or, sorry, don't forget to do that. And also, please do not make them expire, the invitation links, so that way we can get to them when we get to them. Myself and Alex as collaborators, and 3 screenshots are required. One thing that Alex also has asked is please do not attach videos for your labs. They're just little examples of your work. We don't need videos. All we're looking for, this is only good for things like your assignments. Videos are long, and it takes long for us to mark all those things, and there's a bunch of you, and there's only a couple of us. So please only just attach screenshots of your work with a couple of notes maybe, and that's all you need to do to make sure that it's showing off what you're doing. If it's easier for you to make a video than take screenshots, make a video and take screenshots of the video. but don't attach a video. All right, and especially definitely do not attach the entire video for Alex to download. That is a crazy amount of work. All right, also due on the horizon is assignment 3 and 4. I kind of went to the details of these things in a short video that I made for you guys before the break. And I'm hoping that you guys have had a chance to look at these. There's two assignments, assignment 3 and assignment 4. They kind of work together. And there's two different assignment groups for these, assignment 3 groups and assignment 4 groups. I've made 2 groups only because I don't want you, again, to be forced to stay in the same group for a long period of time. So that's why I've made these different group sets. Again, the first one is due Sunday, March 28th at midnight. It sounds like it's far away because we're sitting at March 9th, but actually these 2 assignments are going to really push you to do more than what you've done before. So please, if you haven't had a chance to look at the requirements for the assignments, please do so at your earliest convenience. Start them now if you can, if you haven't started them already. Okay. So we're sitting right now on the week of March 9th or so. We're at March 9th, and we're week 9. And this week we're doing decision making. Neil's asking, is line of sight just one line or a cone? It's up to you, Neil. But we'll talk about the advantage, disadvantage of that. So intro to decision making is now. We're talking about decision trees this week. Next week, we're going into behavior trees. And decision trees and behavior trees are related. There's also directed acyclic graphs, what those are, and how they help us with state machines. So that's coming up. And then you see that in, again, a couple of short weeks, on the week of week 11, assignment 3 is due. Then we get into goal-oriented behavior, some more abstract kind of coding that we're going to be doing over the next few weeks. Because as we get into thinking about goal-oriented behavior in AI, it's not as easy as pathfinding anymore. Pathfinding basically, kind of you have a predetermined condition, and what's happening is, you're moving an object, from a source to a destination node, as an example, across a series of paths. That's really what pathfinding is, and it's predetermined in many ways. But decision making is a lot more abstract than that. And the reason for that is because the AI, your AI agent, can make a lot of decisions based on a number of conditions. And we have to think about what those conditions are. And I'm going to talk about them in lab and as how they relate to your assignment. I'm going to go over the details of that as we go forward. So that is the structure. And then as we roll into week 15, we'll be doing a final test. And the final test will be a little practical test. That's the plan right now. But this may change, subject to change. It might change to a true false multiple choice test at the end. Okay, just let you know as we get closer. Okay, so let's think about decision making for a second as we move forward. So when we think about decision making, there's two types of knowledge, and we're going to talk about this knowledge again. It's not just the first time we're going to be talking about this, and then that's it. There's two types. There's internal knowledge, and there's external knowledge. Okay, so let's think about internal knowledge for a second. Internal knowledge is the character state, health, its own goals, and so on. So things about that only the character knows about, right? And external knowledge is level data and things about other information. Let's think about what these two things are and how they're different. So both of these two things become an input for some kind of decision-making node, okay? And then we have some kind of action request, and we may have, as a result of the action, some kind of internal changes. So changing some kind of character state, health, goals, whatever, as well as some kind of external changes, right? So, world position, those kind of things. So internal knowledge, external knowledge. One thing to note is when we start drawing our level again, and if I was to think about this at a very high level for you guys, let's think about this again, right? So let's suppose that I have an enemy or some kind of AI. And Neil just asked about a line of sight, right? So I have, let's suppose this is my character, and my character is going to have a health bar. Remember what a health bar is. A health bar for a character is a non-diegetic user interface element, right? That basically shows the value of the health element, as an example, or the health property of a person or like a player or an AI, usually above their head, as an example, or near their body, right? The reason why it's non-diegetic is because it's something that the player doesn't normally see in real life, right? So if I don't have a health bar on top of my head or readings for what my heart looks like unless I look at my watch. If I look at my watch, maybe my watch is a smartwatch, will give me things like heart rate and those kind of things. That's diegetic, right? Because I'm actually looking at a device to give me real readings, right? But in a video game, and I'm just putting this out there to you, if you play a video game that is, as an example, that gives you a map location, the map location in a video game, in a mini map or whatever, even if you pull up a world map, is non-diegetic, because unless you have a device that gives you the location of characters and other interesting data in the game world, right? That is something that the player has access to that normally the character doesn't. All right. Normally, if you have a good example is the game Valheim that most of us have been playing lately. And again, just to show you that, I know I've been talking about this a lot, but it's a success story. So we need to talk about this more than more than anything else, right? Success stories, right? So here's Valheim. So Valheim is a crafting survival game, a survival crafting game. As an example, Minecraft with Vikings, kind of. It's very similar to Rust in some ways. There's a lot of other similarities you can look at, but Valheim is a good example of a game where the main character is a Viking, but somehow, non-diegetically, they have access. By the way, sailing on a ship is awesome. Non-diegetically, they have access, to a map of the game world, right? So if you think about this, that doesn't make any sense, from a realistic perspective, right? Where they have access to a map, but we give maps to characters all the time, right? So what kind of knowledge would that be? Internal knowledge or external knowledge? If my character has access to the game world, right? It's external knowledge, right? I have access to something outside of my character. Internal knowledge, again, would be things like health, right? Strength, and a bunch of other stuff. That would be all internal knowledge to the character, right? Knowledge that the character has, right? External knowledge will be something about the game world itself, outside of the character. So let's suppose this is the player. So player P, right? Here's my player. And I'm going to make another thing like this as we draw. Let's just draw some of these things for yourself. You should think about, whenever you think about a level or do any kind of thing with AI, think about, kind of setting up your character and your enemies, and in a very straight way, right? So again, we want to represent our enemies and our player in a similar way. Both of them are going to have a health bar. Let's get rid of this and call it the thing for health bar for a second. Let's do one of these. There we go. Just going to choose a different brush here, and we'll get rid of P, and we'll put in the value of E for enemy. There's my enemy. So we got my enemy and my player. They both look similar, but player is controlled by you. The enemy is the autonomous AI, right? Autonomous character, right? So we talked about a couple of things in assignment 3 that the enemy is going to have access to. One of them is a detection radius that I talked about in my previous video, right? That's the one about assignment 3 and 4. So let's think about that. Let's make that detection radius red, so we can see that where the detection radius is. So imagine if we have a couple cases, again, where the detection radius for my AI, let's say, or my sensing radius is this like kind of red color, right? So anything around the AI, if it overlaps with the player's character, then it's detected. So this is one thing. This would be your detection radius. So we're thinking about the sensing suite that we've talked about before. So the detection radius is one of those things, right? And a detection radius is very good for you, because the detection radius, what it does, allows us, when we do an overlap between the circle and the AABB, that's the player, right? Then if we have this kind of overlap, we know that the player has been detected. So there is going to be a state at one point or another where the player is detected or not. So maybe some kind of variable that's player detected. And we could, normally when we have a Boolean of this type, we say like, is player detected, right? So that's the variable that we're going to keep track of, all right? And that is a variable that's going to be being kept track of by each enemy. Is player detected, yes or no? If the player comes within the radius, that is going to basically check this box. It's going to say that the player is detected. The other way to detect the player is with a array. Usually we call this line of sight. So let's suppose I have an obstacle, right? So here's my obstacle I'm going to draw now. Let's suppose I have an obstacle like so. And my obstacle, let's make it a different color, just so that way we can demonstrate this a little bit easier. So here's my obstacle, and the obstacle, we'll call it obstacle. Okay. And the obstacle is between the character and the player and the enemy. Then, depending on how we do line of sight, if I cast a ray, and think about what a ray is, it's just a line segment, right? A line segment that goes from my enemy to the player. So if I draw it from the center of the enemy to the center of the player, right, do I have a line of sight? And the answer is no, because I passed through this obstacle. Because I'm hitting the obstacle first, and it's the first thing that this line segment intersects with, therefore I don't have line of sight. Neil asks here, he says that, and also Samuel also says some stuff too. Samuel says first, if we had a compass item that pointed north, that would be external too. Well, it's internal knowledge if it's something that's diegetic, right? It's external if somehow you know something that is not diegetic in some ways. We'll talk about that in a sec. But Neil says, you can use the detection radius to detect footsteps too, so the enemy will know the direction based on sound. Yes, you can. Think about this detection radius as a smell radius. The enemy can smell you, hear you. And in Valheim, they also use another way of, I'm saying Valheim because this is the game of the week, kind of thing. In Valheim, they have your character actually, there's wind in the game, and the wind actually takes your scent and transmits it across the wind line. And basically, if there's a enemy downstream of you, then the enemy can detect you based on the wind if you're upstream, right? Upwind, if you will, which is kind of interesting. So that's kind of an interesting way of doing things as well with and another way of detection. Our detection suite for assignment 3 and 4 is going to be two things: a detection radius and some kind of line of sight. Line of sights can be array, right? So we're just going to call this line of sight, right? Line of sight. Could be array, and it could be another shape. It could be some kind of other object that you want to intersect from here, from in 2D between your enemy and your player, right? You've done it with leaving footsteps before. Awesome. Yeah. Anything like that where the enemy can detect or pick up, intersect with anything that it can see, it's kind of an interesting thing. And so the only thing we're asking for in assignment 3 and 4 is, for your sensing suite, is two things: detection radius and line of sight. And this, my friends, is going to be the condition. It's going to represent conditions that you can respond to. Remember, there's internal knowledge and external knowledge. If we didn't do this, as an example, and I could pathfind directly from my enemy to my player without sensing them, it's kind of cheating, isn't it? Right? Because somehow my enemy knows about you, and or knows about the player, and potentially they've never seen the player, right? So that's not what we want to make a game challenging. We want to make it challenging, but we don't make it impossible, right? So the enemy will only detect the player based on their sensing suite. That's what we call it. I'm saying it's called sensing suite, right? And this could include things like, detection radius, which could be smell or, hearing, whatever, some kind of other senses other than sight, right? And then line of sight, which is just sight, right? So that's the, having a couple of ways of doing stuff. That's what the enemy has, some kind of sensing suite, as an example, that gives me detection radius and a line of sight, right? Line of sight can be represented in a bunch of ways. In video games, they can be represented by lines, one or more lines. So, for example, you could create some kind of angle, right, or an arc that you can see. For example, let's say the enemy has a direction they're looking. That's also something that has to be not omnidirectional. Right now, I didn't say anything about the enemy having to look in a particular direction. So if I did that, that makes it even more challenging. So let's do that part. So we'll say that, imagine if the enemy also has a direction that they're looking, right? So wherever the direction of the enemy is looking, then that is going to create the line of sight, right? So if my enemy is looking this way, then the line of sight only goes over here, even though their obstacle, even if there wasn't an obstacle there, if the enemy is looking this way, so some kind of look direction, right? That also is going to be something that that's going to basically be an input for us, right? The enemy is also going to have some kind of look direction, right? Wherever the enemy's looking, that's going to see if they've got line of sight or not, right? And this proposes a problem, right? Because if I only have a single ray of what the enemy can see, right, it kind of makes it so, as an example, from center to center, it's very limited. For our purposes, this is okay. This is good enough to make a line like this. But in 3D, that might be really limiting, all right, in terms of what the enemy can see. And an example of that is if my enemy is in a certain spot, so let's use Blender just as a demonstration of this, right? You can also use Unity, but Blender is just a little faster when we're launching. Eventually, there we go. So here's our cube as an example in Blender, right? And let's suppose that my cube, my enemy is up here in 3D space, right? Here's my enemy, and we have a player that's down here. Let's change the material of the player so we can see the difference between one or the other. We'll call this the player material. Just so we can change this up, let's make this the base color. We'll change to green for the player material, right? And we'll show the player material. Both are green right now. We'll make this one here. We'll use a new material. We'll call it the enemy material so you can see it. In 3D, this promotes an issue, right? I'm just going to put this up there. And let's just say that the enemy material is red. And that's nice. And let's get rid of the player material there so that it's only the enemy material. What happened to the enemy material? Enemy, player, enemy, it's got to be red. I said red. There we go. So, yeah, so in 3D, they're not on the same plane. So if I was to draw a line out from a 3D object, right, as an example, and if it's only in one little ray, then the enemy could be like right up here as an example, and the player can't see it. You know, or the player's down here and the enemy can't see it. That doesn't make any sense. So this is where we think about a cone or a frustum, some kind of other detection methodology that we use. Some people also use other blocks. For example, it could be a cube that can be used to see the player, right? So example, we would draw a new cube. Let's add a new cube in there. And let's move that cube somewhere near the enemy. So we're just going to use the things. Just again, this is just for demonstration purposes on a 3D perspective, right? So here's where the cube starts. And what we'll do is imagine that this is their line of sight. And if I made it so that the cube, and let's just extend it, so we'll scale it only across the z-axis or the y-axis. So imagine the cube only extends in a straight line. So this is where the enemy can see ahead of itself. Again, let's make sure that we're setting it up properly. So the problem with 3D is you see it looks like it's 3D or it's set up properly in 3D, but actually it's offset by some value or another. All right, there we go. Excellent. All right, so as you can see here in 3D, still that would be limiting if you had some kind of cube that looked like this, right? What about the character down here? You can't see down there? That doesn't make sense. It's not proper, right? So of course, this wouldn't be the case, right? The cube could be extended. So let's Control Shift. Let's scale this up so it's more like a frustum. All right, that's kind of like a camera, isn't it now? It looks more like a camera. And yeah, the character isn't being able to see the player because the camera itself, or the frustum that is being displayed, this thing here, right, is the player is not he's not in this volume, right? So in as an example, in 3D, unless the player object is actually inside of the volume somewhere in here, like let's say like this, intersecting with the volume like this, then again, they're not in line of sight. So I'm just talking about line of sight because we were asked about it and it's part of your project. So here's an example where if the enemy uses a frustum of some kind, similar to a camera frustum is like a pyramid with a cut off top. That's what it looks like, right? So this is pretty good in terms of the way it's looking, right? So you can see the player or the enemy is looking at the player, and the player's bounding box intersects with the enemy's line of sight frustum, and so then we have line of sight. Awesome. You can make this a cone. You can make this other shapes. You know, some kind of the simplest one again would be a large cube, right? Anything that's inside the cube, that's where the enemy is facing, can be seen, quote unquote, by the enemy. Neil asks, what about things like Blender? Should we learn that in second year? Again, it's a great tool to learn, but because you guys are in the programming side of the house, then learning Blender is not required. It's something that designers and 3D artists learn, but I think it's great to learn the rudiments of, or kind of the foundation of how to use something like Blender. When you bring things into 3D, you understand everything that artists go through to create them and how to import models. I think this is the good understanding. But beyond that, splitting your focus and learning how to do both programming and 3D modeling might be challenging, especially at the beginning. And I recommend, at least until third year, I would hold off because of the program, the nature of our program. It's nice if you have time in the summer and instead of learning other things, that's okay. But I would probably learn Unreal if I was you in the summer. So I would probably like take the summer to kind of brush up on Unreal, because as we go into your third semester, I believe third and fourth semester is all Unreal for you guys. I don't think it's a good idea to kind of go into it raw. I think there's a great opportunity for you guys to do some pre-learning, and then when you go in and start your lessons, with Unreal in the fall, then you're ready to go. You kind of hit the ground running. All right, so that is that's pretty good. So that's how line of sight works. So again, here's 3 dimensions. We're not talking about 3 dimensions in this course, so it's not necessary. But for now, for us, a detection radius, again, is the ability for us to get external knowledge, so sensing suite, about the world, right, with some kind of detection, where we can also keep track of, is the player detected? What is my look direction? And in my look direction, I'm going to cast my ray, right? So if my look direction is this way, then I'm casting my ray in the direction I'm looking, right? So, for example, even if there is an obstacle here, and let's just redraw this stuff. So we'll get rid of this little line. So the enemy can't really see in this direction anyway, because the enemy is not looking in this direction, right? The enemy is looking in the other direction, down below, right? Over here, right? So let's say the enemy's trudging along and going this way, then they're looking this way, right? So it doesn't matter whether there's an obstacle here or not. However, if the enemy was looking in that direction, so let's suppose the enemy was looking towards the player somehow, moving maybe in this direction towards the obstacle, right? So let's say, or moving down, and the enemy was kind of looking in this direction. This is my look direction, and maybe change from this to that. Yeah. So the enemy's looking in this direction, let's say. Let me make it coming from the enemy middle. So I'm looking in this direction, right? And let's say it would have seen the player, right? But there's an obstacle. So these are the conditions. So I'm going to draw a line again from this point to the player, and you can see that it's going to hit this obstacle, right? So therefore, there's no line of sight, okay? Because that's where the enemy's looking as it's patrolling. Okay, so that's where line of sight's being blocked. Okay, so is the player detected? There's 2 ways to detect the player. Can I see the player? Can I hear or smell or detect the player in another way through my sensing radius, my detection radius? And the radius is a great way of speeding things up. If you only made it so that the player can be detected by sight alone, that could be a very slow game, all right? Depending on how you make your game function, right? If you make the game so that you can detect by overlapping, well, I just heard the player, or I smelled the player, or sensed the player in some other way, right? As an example. And then you can make some rules around this. For example, maybe my detection radius, if my player not only has a health, that's an internal knowledge, but maybe some other internal knowledge, like for example, a stealth ability, stealth level, right? So stealth level could be also internal to the player, right? So my stealth level, if it's higher than my detection radius, my perception, let's look at some external things or internal things for the enemy. The enemy might have a perception score, right? As an example. So let's say some kind of perception level and a stealth level. If my perception level is higher than the player's stealth level, as an example, then the player is detected. That could be a condition. So even if my enemy detection radius, if I don't see the player, right? If I can't see the player, but if my perception is higher than the player's stealth level, then I can detect the player, right? Now here in our game, we're not asking you to compare perception level with stealth level. We're not doing that. We're saying if it overlaps, if your detection radius overlaps, it automatically detects the player. Player has no chance to avoid. Lewis says, please don't, this is how Skyrim happened. Yeah. Yeah, we're not going to make it so Skyrim it's going to be a kind of a stealth game. But yes, we could have something like that, a stealth level versus a perception level. All right. Same thing with an attack level versus a defense level, right? So some kind of attack versus defense. If my attack is high enough, I roll an attack score, random attack, and I roll a random defense into some values, I can have some kind of different damage based on my, first of all, do I get hit? And again, there's other things that you can see as an internal knowledge, like some people show in D&D we use armor class. It could be just defense, some kind of defense level, right? We could have that as an internal piece of information. A defense level, we could have an attack level, right? We could have a, agility level for how fast you can dodge and so on. There could be a lot of things that you can put in here, not just a few different properties of each object. And the more information you have in here for an internal knowledge perspective, the enemy doesn't know what the stealth of the player is or the defense or attack level. They don't know, right? As an example, that is internal knowledge only to the player. Externally, the only thing they can see is what they can detect, radius-wise, or where they can see. Yeah, I just wanted to brief you guys with this idea because it's going to affect you in your assignment 3 and 4. So going back to this internal knowledge versus external knowledge, we need to make a decision based on the information that we have. The autonomous agent will make that decision. Okay. So let's talk about decision trees a little bit. So great thing about decision trees is it's in a tree structure. Now, are you guys taking algorithms at all? C++ algorithms at all? Yes or no? No. Okay. So think about a tree. Neil says he's taken it a bit. Think about a tree structure as, again, made up of different nodes or different leaves of the trees. Think about what the tree looks like. So if I go back to my little drawing, suppose this is our board, right, for a second. And if I think about a tree then, if I'm thinking about the AI's brain, I have kind of an initial decision node. Let's make these nodes a different color. Okay. So here's my initial decision. The tree structure is kind of a collection of objects. All right, if you think about this, right? So a tree has something called a root, right? And the root node, which is this one right here, it has, and we're talking about binary trees for a second. There's different kinds of trees that we're going to see here. The different kind of trees are, so binary trees have only 2 leaves or 2 branches, if you will, okay? And I'm going to draw lines to get there. So again, if you look at the tree structure from here to, let's say, here, and let's say from here to here, right, we have each root has, as an example, 2 leaves. No more, no less, right, in a binary tree structure. And this idea is, as soon as I leave this tree, this part of the tree, this is the root, and I go to this node here, so let's call this node A, right? And this one will be node B. Bear with me, guys, as we build this out. So here's node A, node B of the tree, right? And if I have more nodes here, because each leaf, if you will, if it's a leaf node, each node can have branches of its own. So this is one here, and we'll make another one here, and we'll make another one here, and another one here. And we'll put in some additional little boxes here. So just to code this up here for you guys. And sorry, they're not completely even because I'm just drawing this just like this. And we'll label these things. So we'll say this is C. And notice how I'm labeling it also, right? I'm labeling it in that it's going to be from left to right. There's different ways of doing this, by the way. And it doesn't really matter for us right now, but it will make a difference later, potentially. Okay, so we have a tree structure. And we have the idea of a node, right? So we have a node, right? And we'll call this a tree node, which is the tree node itself is a structure, right? And the tree node is going to have a left node and a right node. So that's the two things it's going to have. So something that's on the left and something that's on the right. Okay, this is in a binary tree structure. So left and right, and each of these left and right are other tree nodes. Okay. There are different kinds of structures here that we have. One of them is this idea of an edge, right? So this is an edge or a branch. Sometimes it's also called a branch, right? And then we have a node. So these are nodes. And there's also, these are special nodes at the bottom, and they're called leaves. Leaves, right? But these are leaf nodes. Leaf nodes don't have any other nodes. They're the bottom of kind of the edge of the tree, right? So an edge or branch and leaf. Okay. In this completely balanced tree, you have really only two decisions you can make. I can do decision A, or I can go to decision B. Those are the two decisions, right? I also want to point out that every tree, every time I go to another node, if the node has one or more other nodes attached to it, leaves, as an example, then we also must think that this node here is a subtree. All right, so this right here is a subtree, right? I'm just putting this out. Okay, here's my subtree. And this node, this over here is also another subtree. Okay, this is a subtree over here. Okay, so subtree over here, subtree over here. And if I had this, if C had two more, that would be also a subtree. Okay, so you can have many subtrees inside of a tree. Okay, because this is like a little tree. It has a root node with two leaves. Okay, so I'm just, am I recording this? Yes, I am. So if you think about this, if you think about this structure, right, that we're seeing right here, really it's about decisions. I can go left or I can go right, right? If I go left, I go to decision A, depending on some kind of condition at the root node, right? I can go left or I can go right, depending on some kind of condition at the root node, right? So really, depending on the condition here, I can go in either direction. Okay, we'll come back to this idea in a sec. So that's the structure of a tree. Think about our tree structure as a custom structure. It's not built into, let's say, C++, although you can download tree structures and libraries that include trees, right? We're going to make our own. Okay, that's how we're going to do it. So again, think about decision trees now. Great way about them and some simplicity around them is they're fast. You can easily implement them, simple to understand, and really modular. And really, every single time, every time we go to a new branch or a new subtree, we're only checking a single condition every single time. Okay. And now let's take a look at the tree structure. It's a tree because we have one start point or root. Each choice is made based on the character's knowledge. So again, is the enemy visible? Yes. Go to this route. Okay. Is the enemy within less than 10 meters away? Right? Let's make this a lot bigger for you guys to see. Is the enemy less than 10 meters away? Yes. Attack. Right? Let's go back up here. Is the enemy visible? No. Okay. Is the enemy audible? If it's not, then you're done. You can't do anything, right? If they are, creep towards the enemy, right? Go back to the top. Is the enemy visible? No. Can I hear them still? Yes. Keep creeping towards the enemy. Go back to the top, right? These are leaf nodes, right? When you reach a leaf node, you exit, right? Kind of thing. Is the enemy visible? Yes, I can see them now. Cool. Are they less than 10 meters away? No, they're not. Okay. Is the enemy on my flank? No. Is the enemy on my flank? Yes. Cool. Move towards the enemy. Exit back out. Is the enemy still visible? Yes. Are they less than 10 meters away? Well, I moved. Yes, they are. Now attack. And you can see how the cycle goes when it comes to decision trees. It's very simple, right? And the advantage of decision trees is that, again, very simple, yes or no. And this is an example of a binary decision tree. There's different kinds. So, like we said before, a decision is made with a decision tree, and you can notice the path, right? Here's the path of all your decisions until you say, well, is the enemy visible? Yes. Are they 10 meters away? No. Here's the path. We'll go here in this particular branch. And is the enemy flank on the flank? No. Are they? Yes. Yes. Okay, cool. Move. And that is the decision that was made. This is the final decision that's made. There's what decisions can be made? Attack, move, attack, creep. Look at these attack decisions. So it's interesting that I can do this decision and this decision. Maybe the way that this root node is created, this node here, is incorrect because I'm saying is enemy on the flank. What does that mean? Does that mean I'm within 10 meters? If it does, if my enemy's on the flank, maybe these are the same things. Maybe I can refactor this tree to make it more efficient. Okay. But what if I have two different kinds of attacks, right? I have an attack that is a melee attack, and I have attack maybe that is a ranged attack. These are different kinds of things, melee attack and ranged attack. If I'm within 10 meters, perform a melee attack. If I'm flanked, and the enemy's on my flank, and I'm within range, attack, do a ranged attack. That can be what this is saying as well. So we can check it in different with different data types. I can use a Boolean, so the value is true or false. I can use an enumeration, some set of values, a matching value 0, 1, 2, 3, 4, some kind of value that I'm checking, some kind of numeric value, as an example, either an integer or a floating point value. If the chance to see the enemy, maybe I don't automatically see you, as an example, like we said before. My detection radius isn't perfect. I don't automatically hear you. I'm within the detection radius, but maybe I got to do a check. I got to kind of roll a dice or some kind of random number and compare that result with my perception level versus my stealth level. So it's not always perfect. And if it's greater than this perception level that I have, or my perception level is greater than the stealth level, as an example, if the player is in stealth mode, right? If they're not in stealth mode, I detect them immediately. He's not in stealth, I can hear him, right? Or them. But if the player is trying to creep around and avoid the enemy, then we have to do maybe a comparison. And so it's not always perfect, right? And this is what this is saying. It could be some kind of numeric value, could be a 3D vector, it could be a lot of things that is a way of us determining if we can detect the player. And then once we have that decision, right, we can decide what to do. Also, one thing to note is if I always made it so that every single time my player detected or my enemy detected the player, they would attack or do something, they become predictable, right? So another thing to do is when we make decisions, we'll talk about this later on in this second half of semester, we may want to randomize what we do. So the enemy might be a different level of enemy. Maybe my enemy brain, as an example, also has a level of its own. So maybe we'll call this the decision level, right? And depending on how high the decision level is, right, of my enemy, maybe they're going to make more accurate decisions based on the information they get from the external knowledge they have from the detection radius and the line of sight, right? Because if the decision level is low, example, a low level enemy, an enemy that's not intelligent as much, right? then maybe what they're going to do is they're going to do something that's wrong. Even though they see the player, maybe they're going to try and go this way as opposed to go towards the player. Or maybe there could be other factors involved too. For example, some kind of morale, right? So some kind of morale level where, some enemies are not as determined as others, right? Some enemies might have a very high morale. They're a leader type, a captain, as an example. And maybe some other enemies have very low morale. They're a rent-a-guard kind of person, right? A rent-a-cop. And they're a guard. They saw the player, but they're not going to attack. They're afraid. Their morale level's low. They're not getting paid a lot of money. So they're going to run away and alert the guards, alert other guards to come. They can't fight on their own. They're not comfortable doing that. Again, you can make as many of these types of conditions as you want, but it's going to come into effect depending on how you set up your decision trees. All right. There can be different kinds of conditions you can match. For example, I can say that if A and B, then I want to do action 1. So both of these have to be true for action 1 to be true, for me to take action 1. Otherwise I do action 2 every single time, right? So if I say no ever, A or B I'm always going to get to action 2. I'm going to do some other action, right? The other way to do is an A or B action, right? So if I'm is then action 1. So if I say yes to action to at the A node, I go to action 1. If I go no, I go to the B node, and if I say yes here, then that's action 1. So either A or B are true, then we still do action 1. So again, these are ways of interpreting or representing conditions, A and B, A or B. And we can combine these things so that the actions make sense in terms of our conditions. Let's think about a decision tree complexity, right? Think about this tree. It's a balanced binary tree, right? Where we have our root node, and I have a subtree here and a subtree over here. And then let's suppose I am on this subtree. This subtree here also has a couple of more subtrees. There's a subtree here and a subtree here. And this subtree has 2 of its own subtrees, a subtree here and a subtree here. So you can see how this works, right? So when it comes to node, a bunch of edges, I have an edge here, 1, 2, 3, 4. So the height of my tree is 4 edges to get to my leaf, the bottom part of my tree. This is in a balanced binary tree example, 4. So if my height is 4, right, how many nodes do I have? How many leaf nodes do I have over here if it's in a binary tree example? Well, think about this. If my height was 1, I would have 2 nodes. If my height was 2, right, my height was 2, I would have 2 plus another 4 nodes, and then plus the root node itself, right? So actually my height is 1, it's 3. My height is 2, it's 1, 2, 3, 4, 5, 6, 7, right? My height is 3, then it's these 7 nodes plus 1, 2, 3, 4, 5, 6, 7, 8, right? So 7, 8, 15 is here. And then these 15 nodes with a height of 4 with another 16 is 31. So 31 nodes total for a height of 4. So you can see how the complexity spirals, right? As it kind of goes up. If I go another level of complexity, then you can see that it's going to add another, let's say, 32 nodes and so on. And it's going to go up in the binary kind of steps. So it's going to go, 16, 32, 64, 128, and so on. And there's going to be more and more choices as you go down, kind of levels of the tree. So there's different kinds of binary trees. One of them is this idea of a deep binary decision tree, right? So where you kind of go in deeper and deeper. There's also a flat decision tree with 4 branches. We normally don't want to program this way, but you could have this too, where you have which state that you're going to be in. Are you going to be in green state, yellow state, red state, or black state? Which state? You're going to take one of these actions depending on the state you're in. Similar to, in many ways, how we use a state machine. This could be an example of how we can convert a state machine into a decision tree, right? So very flat design, right? A deep tree is where we go deeper and deeper and deeper and create, kind of, again, both are unbalanced, where you have a couple of states each, okay? So when we make the decision tree node, then what we want to try and think about is I make a class, it could be, or a struct that's called decision tree node. We define a method called make decision, and the make decision method, it says, walks recursively through the tree, right? Recursively through the tree. And now we have to talk about recursion. Guys, do you know about recursion? How about people who know about recursion? Can you put your check mark on the Zoom call here? Check mark means you know about recursion. X, you don't know anything about it. I'm also checking to see if you're alive. This is your Are You Alive check. Are you alive with me? Patrick says, is that what a function calls itself? Samuel says, a little bit. Anyone else? You can, instead of the chat, if you can put a check mark. I'm not looking at your images here, so the only thing I can see is the participants panel right now. Ruben says a tiny bit. Okay. I got Andy. He says he understands what a recursion is. Niels understands it, and so does Eric and Chicane. Okay. So think about what a recursive function does. Let's talk about this a little bit before we move on. Again, I'm just going to use my drawing for a second. So I'm here in the root node, and the question is this. Here's my condition. If I have a leaf, if I have two more nodes and they're not leaf nodes, right? If I'm not a leaf, here it is. Here's the end condition. If I'm not a leaf, travel to my, go to my my left node and my right node. If I'm not a leaf, okay. So I'm not a leaf. Go to my left node and my right node. Go to my left node. I'm going to my left node. Cool. If I'm not a leaf, go to my left node and my right node. Go to my left node. If I'm not a leaf, I am a leaf. Okay, do my action. Right? Do my action. Okay, good. Now that I'm done my action, go back up. Okay, good. If I'm not a leaf, go to my left node, then my right node. My left node is finished doing its action. Now do my right node. Okay, cool. If I'm not a leaf, okay, I'm done both these actions, go back up. If I'm not a leaf, do my right node or my left node. And this is how it would traverse back and forth, right? And then finally this up here. So now I've traversed the entire tree, starting with the left subtree. Again, it really depends on what you want to do. You can start with the right subtree and then go to the left. But this is a way of recursively going from traverse the tree from one node to the other, okay? Now this is trying to get to every node, right? But here's another thing I can say, going back to what we said before, when I recursively go through the tree, right? When I say recursive, I mean, I want to go back. I want to kind of complete. I want to send a message from one part of the tree to the other part of the tree, all right? So let's say, for example, I'm going to return out the action that I'm going to make to the calling function. So let's say, for example, I call the decision tree, right? The decision tree is going to return an action. We don't know what the action is going to be, but it's going to have an action class, whatever that action class is. And the action class is going to be an abstract class, right? So it's going to be an abstract action class, which means I don't have a specific action that I'm going to take right now, right? The action class has some kind of action, whatever it is, and maybe it'll have some kind of execute, right? I can execute that action, right? Whatever the execute function is. I don't know what it is, but it's going to be some kind of execution function that we're going to have to use. All right, we have, let's make another kind of class that's here. Let's call this the patrol action. Notice I put action in the name of the class. Patrol action extends the action superclass. Okay, patrol action extends the action superclass. All right, and the patrol action, because the superclass action has an execute function, then I can override the execute function, and I can override the execute function inside of my my patrol action to do whatever it's going to do. All right, that's how actions work. So what I want to do here is I want to return the action that I'm going to take from my decision tree when I come into the decision. So again, I don't know what decision I'm going to make, but at the top, I'm going to also have some kind of condition. So maybe I'm going to have a condition class. And my condition, right, my condition abstract condition class, we'll say, abstract condition class. If my abstract condition class, it's going to have some kind of comparison, right? I'm going to do a comparison or some kind of, you know, I'm going to look at the condition, whatever it is. So let's say, for example, we're going to call this the comparison. Compare. I'm going to compare A with B, whatever those things are, to come out with a condition, right? Conditions can also be different types. So this is another kind of class, right, as an example. So two types of classes, an action class and a condition class, right? So let's suppose I have another class for the condition. I have a, do I have line of sight? That is a condition, right? So line of sight is a class, right, that inherits from the condition class, right? And I can compare, I can do a check or a comparison, right? That do I have line of sight, yes or no, right? It's kind of and it returns some kind of Boolean, right? Usually a condition says it's true or false. I passed or failed, right? As an example. All right, so that's kind of how it works. So let's say this is a Boolean type condition. There could be other conditions too, a float type condition, where I can compare two floats or whatever. But this Boolean type condition is something that I can use. So the patrol action, let's suppose I don't know which action I'm going to take, but the condition might be, do I have line of sight? Do I have line of sight would be at the root node. So line of sight, right? Let's build this up here for a second. If the answer is yes, right? Let's say yes is always to the right and a no is always to the left. If I have line of sight, what do I want to do? I want to check to see if I'm close enough, right? So along this edge, maybe there'll be another condition that says, am I close, right? So close, that'll be a condition class, right? To compare how close I am compared to the enemy. Compare, right? I'm gonna return a Boolean. I'm going to do some kind of, whatever my execution is going to be for my condition. If I'm close, it's going to return some kind of information back if I'm close or not. Close, so that's going to be over here. If I'm close enough, what am I close enough to? Is it close to melee combat or not? If I am, yes, then attack. Okay, attack is going to be an action. Because now, let's take a look. We're at the leaf. We have two leaf nodes. Now I can only take two actions. Action on the left, action on the right. So if I'm close, then I'm going to do the attack action, which is an action type. And I'm going to override my execute from my attack. I'm going to execute my action, right? Whatever that action is, all right? So I'm building up a set of classes that are conditions and a set of classes that are actions. And when I build up these two set of classes, then I can take action at the end. So action will be the attack. All right. So there's my attack. And what I'm going to do is I'm going to bubble back up. I'm going to say that the attack action is what I'm going to take. Cool. Let's return the attack action back to the root node. Let's return the attack action back to the calling class, whatever that is, to make a decision. So the attack is what I'm going to do. And then I've finished off this route. Okay, what about if I'm not close? I have line of sight, but I'm not close. Then maybe I want to do the move action. So I want to move. Okay, again, I'm looking through decision trees. So there's the move action. All right. All right, I move. I go back up to here. I'm not close, right? I'm going to do the move action, pass to the root node. I'm going to do the move action, pass it back up to this is the recursive nature. Pass it back up to the calling function, whatever that is. Move action is the action I'm going to take. Okay, so really the decision tree is going to return a move, right? Or decision tree will return an action. It's going to be given a set of conditions, right? and it's going to return an action. That's what it's going to do, whatever the action is. Okay? Cool. Let's keep going with this scenario. Okay, do I have line of sight? No, I don't have line of sight. I'm here. All right. The other one is, can I detect the player? Right. So, is the player in detection radius? Is the player detected? Right. So that is another condition. So the player is overlapping with my detection radius. Yes or no? Right. So no. Keep patrolling. That is my patrol action. Patrol. Return the patrol action. Back out. All right? So keep patrolling. Yes, the player is detected. Okay, I want to move to line of sight. Move to line of sight. That's the action. Move to line of sight is the action that I'm going to take. Okay? Again, this is assuming that the right edge is always yes, and the left edge is always no. Okay? Are we using composition to have these in the enemy class? Yes. Absolutely. Okay? Does this make sense to you guys? So again, when you think about this idea, right, you pass back up the tree, whatever calls the tree itself, you're going to pass back up the tree the action that is executed. I'm going to execute the move to line of sight action. That's the action. I'm going to pass that back as a function, right? Okay, what's the action here? I want to pass the move to line of sight. That's the decision. I'm passing that back up to the root. Okay, move to line of sight. That's the action. Okay, I'm going to pass that to the calling function. So my decision for this round is move to line of sight. Cool. I execute move to line of sight. All right, and then I come back to the decision tree again. It comes back to the next round. And usually, guys, you don't want to do this stuff here every frame. You want to do it so that it's like a bit of a delay. Maybe it's going to be every 20 frames. Maybe it's going to be every 30 frames. If it's a 60 frame loop, you don't want to do this every single frame, right? Because if you do it too many times, you're going to get jitter again. You don't want jitter. You want to slow things down a little bit, right? So if I'm here and I come back to this point. Okay, do I have line of sight yet? I moved to line of sight. Do I have line of sight? I thought I had line of sight when I moved here. I came to a node that had line of sight. You know, I attempt to move to line of sight. Well, do I have line of sight yet? Yes. Good. Am I close? No. Move closer. Okay, that's my next action. Move closer. Moving closer. Okay, cool. I'm back to here again. Do I have line of sight still? Right? Yes. Cool. Am I close enough? Yes. Attack. Pretty simple. All right, so that's how it works, the decision tree. Okay, so that is what we're talking about here. So again, we start off with the decision tree. The decision tree is going to make some kind of decision. It recursively walks to the tree. We have an action class that has a decision to make, right? Makes the decision. I like to see that it executes the action, whatever the action does. It's going to execute action, right, as an example. And then what happens is each decision, right, as an example, is there could be a true node and a false node. The true node is the node, let's say, on the right, and the false node is the node on the left. If it's left, it's false. And by the way, that's another thing that the decision tree can return. Instead of returning the action, right, the other thing that it can return is true or false. Do I have a true or false, you know, somewhere at the bottom here, right? So example, did I attack? True. I can return that out. It can determine if the action, the action that I'm getting back is the correct action. All right, there's different kinds of decisions. I can make a floating-based decision where I get a branch. So this is the type of decision that I can make. So this is a derivative. It derives from the decision, right? And I have two values, a min value and a max value, where I compare the min and the max. Remember the compare idea? Min, max. I compare those values. And if my value, whatever the value lies between min and max, then I make that decision. So whatever my test value is, right? And then I either return the true node or I return the false node. So true and false node is the action I'm going to take. So again, if am I within range? That's a floating type decision, right? Am I within range? What's the minimum value? What's the maximum value? What's the range that I'm looking at here, right? Is it maybe I have a minimum value, maybe I don't. Maybe I just have a maximum value. So if my test value is less than my maximum value, then I'm within range. We don't care about the minimum value. Maybe my minimum value is is 0. So that could be the minimum value. Sometimes you use minimum and maximum values for things like a ranged attack. So there could be different kinds of attacks, and in your assignment, in assignment 4, you have to do two different types of attacks. A melee attack, right? That's an action, right? And there could be a ranged attack action. Those are two different attack actions, or two different actions. And because they're of attack type, maybe you can have a subclass of attack action. Attack action could be an abstract superclass that also has an execute, but now we're going to do a specific melee attack action or a ranged attack action, right? Whatever that is. It could be like that. But the melee attack action, in order for us to get there, maybe the distance has to be less than, or let's say within, let's say 5 feet. So if I'm within 5 feet, or let's say, I don't know, whatever feet is in your structure. So let's say, for example, you have X number of pixels per, per meter, or X number of pixels per feet, depending on how you want to scale out your grid. Let's say, for example, there are, 30 pixels per foot, right? 30 pixels per foot, as an example. So that means if I'm within 150 pixels, I'm within 5 feet. That's what this would mean. But if it's something like, 5 pixels per foot, then it would be within 25 pixels. If I'm within 25 pixels, right, as an example, where 5 feet, where each foot is represented by 5 pixels per foot, right, as an example, then I can attack. I can perform a melee attack, whatever that is. Okay. And a ranged attack, there's going to be other things that are going to come up. Maybe I need a minimum distance, right? So I need to stay away. I want to keep the player away. If the player's too close, I can't do a ranged attack. It's like trying to fire a rifle when the player's trying to attack me with a sword. It's very hard. I'll have a disadvantage somehow, right? So there might be a minimum distance that I want to be away. Let's suppose I need to be at least 10 feet away, 10 feet, where it's 5 pixels per foot, let's say, as an example. And maybe I have a max distance of maybe I have a shotgun or something like that, or another small range weapon, where I don't want to be farther than 20 feet. So it's going to be some kind of, again, between 10 and 20 feet. And I want to maintain that distance, right? As an example, some kind of minimum and maximum distance. I'm going to maintain distance. I can be as far away as 20 feet, but I can't be closer than 10 feet. Okay, different types of comparisons that we can make. Okay, again, I'm using this as my whiteboard, so forgive me. Imagine if I was doing this. Sinan says, can we randomize it? Sure, you can randomize whatever you want, but just be careful. You randomize this, you mean, or randomize this? It's up to you. So that's what the decision nodes might look like. Okay. Again, I want to make a decision. The make a decision method might be something where I take an action. All right. So it really depends on how you want to see this. I think about them as actions. I want to execute the action or make a decision. It's up to you how you want to see them. Right. One thing is what it says here. Decision trees are definitely designed to be fastest when they're a balanced tree. So here's an example of an unbalanced tree. And here's the balanced tree. Why is it balanced? Think about a sort algorithm here. I want to, kind of get the, I want to make either a right or left decision here. I want to go right or left. I don't know which one. I can only make 2 decisions, right or left. And then each decision that goes underneath it, because this can be quite a complex decision. So again, here I can say, do I have line of sight? Yes, I want to go to the right. No, I don't have, I want to go to the left. Okay, cool. I have line of sight. Am I close enough? Yes. Right? Close enough to what? Close to melee close? Right? Yes. Cool. I'm here. Maybe there's going to be another condition here. Do I have ammo? Am I loaded? Do I have my sword in hand? Yes, I have my sword in hand. No, put my sword in hand. Like draw my sword, kind of thing. That could be the next level of decision. Come back out. Okay, cool. Do I still have line of sight? I drew my sword. Cool. Yes, I do have line of sight. Am I close enough still? Yeah, the player didn't move. Cool. Is my sword out? Yes. Attack. Draw my weapon is one action. Attack is the other action, right, as an example. And so you can have very complex decisions because they're composed of the entire part of this tree. This part here is the way we're going to make one of these decisions. We have a number of decisions here that the AI can make, right, from A to H. Okay, and this is an example of a very quick decision-making algorithm. Here, not a great idea because I need to check each individual node as an example to make every single decision. So I'm going to make 1, 2, 3, 4, 5, 6, 7 checks, right? As an example, if I want to get to H, every single check, I got to check each node, right, in an unbalanced tree. Here, I make 3 checks, right? So much faster than this. All right. Sometimes you have a situation where you want to merge branches. So I have a branch here and a branch here, but they lead to the same spot. This could be okay, right? This is kind of a so-called pathological tree where I kind of go back to the previous branch, right? A good example of this would be a cave structure, all right? A cave. I'm going to use a decision tree to create a procedurally generated maze or something like that. Okay, cool. I go into the maze. I'm in my start node. Cool. I want to make a either a kind of a door, or I want to make a corridor. Which one do I make? Door or corridor? Okay, corridor. Cool. Am I going to make a corridor that goes straight, or am I going to make a corridor that goes back? All right, corridor that goes back. Cool. Corridor that goes back. Does it lead to a room, or does it go to a cavern? Right. Well, it goes to a room. Okay. Cavern. Maybe this one also leads to a cavern. So you can make some kind of, procedurally generated maze with things with merging branches. Typically, we don't merge branches unless you want to do things like refactoring, where you want to reduce some of the actions that have an, you can take based on you're coming up with the same action, just like we did earlier, where I'm still going to attack no matter what I do. And I think if you have this situation, you may have an opportunity for you to redesign your tree. And I recommend when you think about your AI, you design your tree ahead of time before you program it. All right. Random behavior definitely adds unpredictability, and I like that. We talked about this before. Neil says we did binary search algorithms. That's good. If you did binary search algorithms, then you know that's why we do them. We do them. So here's an example of this, right? I could flip a coin, right? So am I under attack? Yes. Defend. No. Okay. Well, now I'm going to flip a coin. Instead of me having to make a decision on what to do, right? And, I'm in patrol mode. I could stand idle as an example, or I can continue patrolling. Random action, heads or tails, 50% chance, right? Or you can make it so that there's someone who's more principled. As an example, maybe there's going to be a guard with a higher morale level, a higher guard level that is always going to be on patrol mode, right? And maybe that higher guard level also has a higher perception, so they can detect if the player is trying to stealth and hide, as an example. Okay, so that is some randomization. Otherwise, what's going to happen is if we have 100% decision, I'm going to attack. I'm going to do this. I'm going to do that. It makes it so that, like I said before, that the AI becomes very predictable. So again, we can do random decisions instead of predetermined or static decisions. And that's your decision tree. All right, questions around decision trees. So I think we've kind of gone through the basics of them for the most part. One thing to note is what I shared with you guys before on the previous video. So I made a video, and for those people who haven't seen it, please take a look. I mean, again, it's not going to be, I'm not going to tell you it's going to be the video of videos or something crazy. We're not talking about that at all. But what I want you to see is something that looks like this. So here is the scenarios that we talked about in the video, right? Or that I did in the video. So one scenario, what video? There was a video that I made that is posted on Blackboard. Let me just go here and close this off. And no, we don't want to do this. And if you look up on Blackboard here, guys, so let's look at Blackboard, not Valheim, Blackboard. And if you look back at lectures, and if you go back to week 7, there are 2 videos that I made in week 7, the week of your test, right? One of them was assignment 3 details, and the other one was assignment 4 details, right? And I also kind of talked about assignment 3 and 4, and assignment 3 and 4 are now posted under assignments, assignment 3 and assignment 4, okay? One thing I've also done for your assignments is please take a look at the groups that I've created. So I've got assignment 2 groups, right, as an example. And I've also got assignment 3 groups. And I've also got assignment 4 groups, okay? I've done this so that way you don't have to be stuck with any one of your group members that you have today. So if you're working in a group member with groups, by the way, assignment 3 and 4 are groups of up to 3 people. That's 3 people that you can work together, right? So let's suppose you work with 2 other members, and those 2 other members in assignment group 3, you're not happy with them, as an example. And what you want to do is you want to kind of move out of a group, and in assignment 4, you hook up with other people. That's totally cool to do. I'm fine with that, right? So that's why I've created assignment group 3 and assignment group 4, right, for you to do that. So that is how this works. But what I did was I shared with you guys a little bit of a diagram similar to this. I'm going to just kill this because hopefully you got all this already. But this idea of a sensing suite and the different actions and everything else you take, it's on the video now. Let's make a new diagram. And I'm going to see if I can just drag and drop this one. So there's the diagram that I was going to use before. So the scenarios that I talked about in the video are the following. If this is the player, right, in your assignment 3 is going to have 4 different cases. Case 1, the enemy is going to have no line of sight and no detection radius. So line of sight is false, radius is false. That's one type of case. Case 2, line of sight is false, radius is true. Player can be detected. Case 3, line of sight is true, radius is false. And case 4, line of sight is true and radius is true. Those are the 4 different types of cases that you can have in assignment 3, where the enemy can be at different positions relative to the player, and they can have they can detect the player in different ways. Okay, based on if the enemy detects the player, you have the ability to use whatever means necessary for you to get to the player. And if you look at your documentation that I've shared with you for assignment 3 and assignment 4, if you look at assignment 3 criteria, we're starting to look at different scenarios. So assignment 3 is really a setup assignment where you set up your debug keys. You can use debug keys, or as an example, you can also use IMGUI. It's up to you, whatever works best for you as an example. But basically what you're doing is you're setting up obstacles and something called a base enemy, which we're going to talk about. Some kind of base enemy with detection capabilities, all right? And basically what you're doing for assignment 3 is it's all setting up for assignment 4, right? That's it. It has the detection radius. You should check it out. You should make sure that it works properly and that you have the ability for you to do line of sight. That is what we're going to be working with in the lab coming forward, okay? But assignment 4 is really where we want you to use everything. And this is where it becomes more interesting. And from what we talked about today, and I'm going to stop here after this. I just want to talk about the decisions that your AI can make here. So now assignment 4 is around AI behavior, right? So let's think about this for a second. Here are the AI actions. Patrol, move to player, close combat attack, flee, move to line of sight, move to range, move behind cover, wait behind cover, ranged attack. You can have other ones as well. But these are the different kinds of actions that any AI can take, okay? And you're going to have two loadouts. You're going to have a close combat enemy in assignment 4, as well as a ranged combat enemy in assignment 4. Depending on the loadout, they have different action capabilities. One action capability for the close combat enemy would be the close combat action, whereas the ranged combat enemy can only do a ranged attack. One thing that you could also create is a hybrid that can do both a close combat, as well as ranged. This is not something that we asked you to do, but if you wanted to add that in as a bonus, then I would entertain that if that's what you wanted to do, where the enemy can do both. And maybe it'll do different things based on their ranged combat ability. You could add other things in here than what we've added in. But this is the basis for what we want you to do for assignment 4. So you need some kind of decision points, and you need to be able to think about, how are you going to make your decisions? Can both enemies use same sprites, different animations? It's really up to you. I highly recommend making it different sprites. It'll make it more interesting for yourself. For example, maybe a ranged combat enemy is going to have I'm just thinking about, again, some kind of fantasy type game where you have ranged combat enemies might have bows and close combat enemies might have swords, right? As an example. So could you show the same body and then just put a sword or a bow? Yes, you could. But you definitely want to have different animations for each. A different animation for the sword strike, and a different animation for the ranged attack, whatever that's going to be. Okay, so 2 different loadouts. And these 2 different loadouts, when you make your game, are going to be things that we're going to use. We're going to use the sensing suite to detect. And so think about the environment here. If the close combat enemy has line of sight, perform move to player action, right? If the enemy has line of sight and is within close combat distance, whatever that is, perform the close combat attack, right? So those are the things that we're talking about. Sprites are tiny, so the map is big. Is it okay that they are really small? You can still see the actions. I mean, again, Neil, it really depends on, I'd have to look at it from a case-by-case basis, but yeah, if it makes sense, I'm okay with it. If your grid is very, very small, then that is going to make it so that the enemy has to be very small. Okay. I would make it so it's more usable. You might want to make your screen larger for your game, and make the grids a little bit larger too. Okay, so that is the idea that we have here, and this is how it ties into what we're doing for assignment 3 and 4. So this is the first thing. So today's lab, what we're going to be doing later on in about half an hour or so, is I'm going to start with line of sight. How do I do line of sight? How do I detect line of sight? And also, how do I start detecting the radius? If I can get line of sight and radius set up, once I have that, then I can make decisions, right? All right, any questions around the stuff we talked about today, which is, so far, it's all around decision trees. So decision trees is what we covered. And we covered the idea of making decisions based on simple, binary decision trees. And I recommend you stick to binary decision trees, guys. Don't go really beyond that for this point. Keep it simple. And if you keep it simple, if you use binary decision trees for your game, it's up to you. By the way, you don't have to make it a decision tree if you don't want to. I'm also going to say that there are different options. Think about the things we're learning over the next few weeks. One of them is decision trees. There's also something new called behavior trees next week. And then finally, state machines. Okay, state machines are probably one of the easiest ways of doing things, right? State machines and decision trees, they're the 2 most common ways of making decisions for an AI. When we spoke to Ubisoft at Ubisoft Night last year, when they hosted their Ubisoft Night, they mentioned that all students should know how to use decision trees. So I recommend decision trees and state machines. I'm not saying that behavior trees aren't good, Behavior trees are kind of a different form of a tree, but behavior trees are more complex and usually for a more advanced goal-oriented behavior. Okay, we'll talk about that later on. So more of an advanced AI. Okay, any questions around the stuff that we talked about today before we go for the day? Until I see you guys in lab. Sinan says, state machines that we use for scenes? Kind of, yeah. Yes. Neil says, is state machines using enums and jumping around to different positions in the enum states? Yes, but there's also something called hierarchical state machines where you have one state machine within another one. It can be quite complex, and you can have transitions. So you go from one transition state to the other. Dylan says, how do you make GitHub invite that doesn't expire? They shouldn't expire unless you otherwise say they do. Neil says, that is basically what I did so far. Yeah, so, I mean, I think you'll have more success, Neil, with decision trees. Decision trees are far simpler. One thing to note is you can make a state machine into a decision tree. You can convert one to the other, right? But you can't, it's going back the other way that is the problem, right? Making a decision tree into a state machine might be more challenging. So just, actually both ways are pretty tough, depending on how complex your decision tree is or your state machine. Okay, any questions around the stuff we talked about today for decision trees? If there isn't, then again, when we look at our schedule for today for the labs, here is the schedule. So for today, we have our first lab happening exactly at 12 o'clock. So that's within about half an hour. And the next lab happens at 4 o'clock today. So people who are meeting me at 12, that's in half an hour. I'll see you soon. We're going to start talking about line of sight. How do I run animations from the actions and conditions? You trigger them, Neil. That's what you'd basically do. So you'd have an animation triggered from the action that you're doing. So if you have an action, you're going to trigger that animation. Okay, it's usually the actions that trigger it, not the condition. Okay, any other questions before I move on? All right, guys, thank you so much for attending lecture. I'm going to see you guys at noon for the people who are with me at noon for the first lab, and then I'll see you guys at 4 for the second lab. Remember, Alex's lab happens on Fridays. Please make sure you attend your labs. Thank you so much, and I'll see you during lab. Thanks, guys.